hope with the highest of hopes that I never have to go back to the trap, and my days are dealing with dope. So I only spit fire and dope. So later on you can go quote my lines to your people and folk, and they say, dang, that boy be spitting that pressure.
Okay, on to chapter 2. We're going to do 2.1, which is called derivatives, and we've actually talked about derivatives in the last chapter. So chapter 2 is in some ways the most important chapter of the entire course. You need to master chapter 2 to have any hope of being successful in calculus, except for one section. This one, 2.1, yeah, it's a really important section, very important, but it's section 2.2 onwards that has all the processes, the skills that you must master to be successful in the course. But this is important too, don't get me wrong. Alright, in the previous chapter we said that the derivative of a function f at a number a is equal to this. Now, I don't think I used this notation before, this f prime. This will be the first time we've done that. That signifies a derivative. So this means the derivative function of a is equal to the limit of f of a plus h minus f of a divided by h as h approaches 0. And remember we found this was the difference quotient, right? And we found another one which was f prime of a equals the limit of f of x minus f of a divided by x minus a as x approaches a. So these are your two difference quotients. And a couple reminders here. Well, I guess one reminder would be that these are the difference quotients. And the other thing I wanted to remind you is what a is. So a, what am I going to write? So I'll put it here. A is the x value of the point you are interested in. You are interested in. Okay, so there you go. And the one new thing we have so far here is another way of signifying the derivative of something is to say this f prime. That means the derivative. And in this case, the derivative is expressed as the difference quotients. This is one way of expressing the derivative. Okay, now here's some more review for you. Geometric interpretations of the derivative. When you find the derivative of something, what are you finding? You're finding two main things. This is really a critically important section too, because you have to keep this in mind. It would be ridiculous to get through this course and not to realize that when you find the derivative, which you are going to find hundreds of times in this course, when you find the derivative, you are finding the slope of a tangent. So it's the tangent line to the curve y equals f of x at the point a, f of a. I hope that makes sense. That's the y value, because if the x value is a, the way you would get the y value is to plug a into f and get f of a, and that this tangent line has slope f prime of a, right? So if we had some function and we have some point right here, and the x value of that point is a, and the y value of that point is f of a, and if we were to draw the tangent line, that looks pretty much like the tangent line right there, and we were to find the derivative of this function, whatever this function f is, if we found the derivative of f, in other words, if we found what f prime is, then what we would find for the answer to the derivative of f prime of a would be exactly the slope of this tangent line right there. Okay? So when you find the derivative, you find the slope of a tangent. The other thing you found is you found a rate of change. Remember we talked about instantaneous rate of change. So the instantaneous rate of change of y equals f of x with respect to x when x equals a is equal to f prime of a. So same sort of thing, when you find the derivative, you are finding the instantaneous rate of change at that point x equals a. Slope of tangent, rate of change. Got to remember that. You have to remember that. Okay, there's another way of thinking the derivative. The derivative can be thought of as a function because the derivative varies from place to place. Like at point A here, this was the slope of the tangent. If I picked another point over, I don't know, here, and called this point B right here, had an x value. If I was to draw the tangent of that one, it would be a lot different than this, wouldn't it? The tangent of this one would go something like that. If I was to pick the point way up right at the top here, point C, let's call it, the tangent line would be something like this. So you can see that all the different points on the function, the main function, have different tangent lines. So for this reason, the derivative can be thought of as a function as well. The derivative of a function varies from place to place. I've just shown that. Different points have different tangent lines, and the tangent line of the slope of a tangent line is the derivative. So the derivative of a function varies from place to place. In fact, the derivative is a function itself. So given a function f, the derivative of f is the function f prime, and this is defined by the following. F prime of x is equal to the limit of f of x plus h minus f of x all divided by h as h approaches 0. Now this should look very familiar, but not exactly the same. But if you compare that to this up here, I'll just highlight it, this up here, it's pretty well exactly the same, isn't it? The only thing different is that we have a plus h and a here, and we have x plus h and x here. Why is that? Because in this equation up here, we had a certain point a, which was the x value of the point you're interested in, right? In this this formula here, the x can refer to any single one of the points on this function. It could be the a, it could be the b, it could be the c, it could be this point out here, it could be this point here, right? So the highlighted one only referred to one point. This function works for any point you want in there. You can plug any x value of any of these points into there. Okay, so here's what we're going to do. We have a function right here. This is f of x, and we're going to sketch the graph of f prime of x. In other words, we're going to sketch the derivative as a function. So remember, what we're looking at for the derivative is the tangent lines of every point on this graph. Now, I do not want to pick every single point on this graph and draw tangent line, tangent line, tangent line, tangent line. That would take us a long time. But there's a few points on that graph which would be very easy to graph the value of the tangent line, the slope of the tangent line. Can you think of them? This, for example, would be a very easy point to pick. How come? What's the tangent line look like there? The tangent line would look like this, a horizontal line. Sorry, it's so thick. And what is the slope of a horizontal line? The slope is 0. So at this point, which is somewhere between 0 and negative 0.5, so between 0 and negative 0.5, our slope of the tangent line is 0. Do you see any other points that are like that? Absolutely. This point right here has a horizontal tangent line. So the tangent line has a slope of 0. So at that point, which is about 1.25, again, it should be at 0. And there's one more right there. It has a tangent line with a slope of 0. So at 3, it should also be at 0. Okay, let's get rid of those for a second. So before we hit this point that had this matches up with this slope of the tangent line right here, let's take a look at the tangent lines on this side of it. Tangent line would look like this, and this, and this, and this. Okay, what do all those tangent lines have in common? Those are all negative values. And you can see as we move along here, we're getting less negative and less negative and less negative. Now, I'm not really worried about you getting this perfectly, like whether it starts here or here, but what's important is you realize that it started in the negative and it got less and less and less negative until it got up to 0. So it's going to look something like this. Okay, now from here to here, I'll do it in a different color, let's do it green. What happens as we go from here to here? Well, at first the tangent lines look like this, and this, and this, and they continue until about right here. And what's happening to them? They're getting bigger and bigger positive slopes. So from this point up until just before 0.5, I guess, you'd expect them to be getting bigger and bigger positive. Again, I don't know how high it's going to go, but I'm going to draw something like this. Now, what happens, I'll use blue here, what happens after we get, after this point right here? If I draw the tangent lines like this, like this, like this, like this, like this, are they positive or negative? They're positive, but how are they differing from the green ones? These ones were getting bigger and bigger and bigger. These ones are getting less and less and less. And that's good that they're getting less and less and less. They're becoming less and less positive all the way down to 0 right there. So they should be getting less and less positive all the way down to 0 right there. Okay, it's going to be very similar now. I'll use purple. If I draw tangent lines, it's going to be negative, even more negative, even more negative, even more negative, up to about here, right? They're getting more and more negative up until about 2. So again, it's coming down. I don't know how low, it doesn't matter. Let's just go to there. And after that, it's still negative, but they're getting less negative and less negative and less negative and less negative and less negative, all the way until we get to this point when it's actually horizontal. So this is good because it's getting less negative and less negative and less negative up to 0. And finally, I'll go back to green again. We're getting positive, more positive, more positive, more positive. So we're just increasing positive after that. So we've done it. Oh, it's very colorful. It's very beautiful. We've taken our function. We've considered the slopes of the tangents, and what we've graphed is the slope of the tangent lines. Have I nailed it exactly? No, but I definitely have the general sense, and you definitely want to nail this point, and this point. Sorry, we're doing renovations, and I have no door on this room, and so you're hearing everything. You can hear Sophia, her boyfriend's here, a big party going on downstairs, and here I am doing math videos. Pretty sad existence, eh? Okay, so sorry for the noise in the background. Next page. Ways to show the derivative. So this is important. This is how you represent that you're talking about the derivative. So one way you can do it is you can say f prime of x. That means the derivative of the function f. Another way you could do it is y prime. These are both probably the most common, really important that you know that. The third one I would say is equally as important, is this one, dy dx. Now you got to memorize these three or recognize those three. You have to know that those are derivatives. The rest of them, these other three I'm going to show you, are not nearly as common. So there's d dx of f of x. That one, yeah, I saw that at university. I remember that one a lot. I don't even remember these last ones. A capital D of f of x, meaning the derivative of f of x, and capital D with a little x of y. I've never seen that before I saw this textbook, I think. So these three in particular are the ones that you need to be familiar with. These are ways of designating, hey, I'm talking about the derivative here of f. I'm talking about the derivative of y. I'm talking like that, okay? Ways to denote the value of a derivative at a specific number. So this is like your general derivative. How would you guess that you denote the derivative of at a, at the point that has an x value of a? Well, this one's pretty easy. You would do f prime of, you wouldn't put x, you'd put a. Another way we could designate this is dy dx, just like we had here, but you put this square bracket and then say when x equals 2 or 3 or 4 or whatever, we'll just put a. And the final way, which is very, very similar, is dy dx, just a line, and then x equals a. To be honest, this is by far the most common way you're going to see it. Okay, but these other two, yeah, I've seen those ones as well. All right, if f of x equals x squared minus 3x, find f prime of x, then use it to find f prime of 3. So what we're going to do is use our derivative formula. So that is this blue formula down here. That's what we're going to use. So I'll rewrite it here. F prime of x equals the limit of f of x plus h minus f of x divided by h as h approaches 0. Okay, the limit, just put the h approaches 0 again. So what we have to do is we have to plug x plus h into the function. Here's the function right here, right? The x squared minus 3x. So we're going to have x plus h squared minus 3 times x plus h. That's the first bit. Then we're going to subtract, and what we're going to subtract is f of x. Well, f of x is x squared minus 3x, and we're going to divide all that by h. Alright, now it's just straight algebra. X plus h squared, well, that equals x squared plus 2xh, or 2hx, I guess if I put it in alphabetical order, and then h squared. Distributive property here, I have minus 3x and minus 3h, minus x squared and plus 3x. When I do the distributive property here, all divided by h. This is the best part because a lot of stuff will always cancel. X squared, negative x squared. Negative 3x plus 3x. Okay, we're just left with two terms. You can factor an h out of both of them. So that'll be the next thing we'll do. We'll have the limit as h approaches 0 of h. We're left with 2x. Oh, with three terms left. I'm sorry, with three terms left, and you can take an h out of each one. So 2x plus h minus 3, all divided by h. You can cancel out those h's, and you're ready to evaluate the limit. How do we do that? We just plug 0 in here to all to h, right? As h approaches 0, so we're going to plug 0 into the h. So we get 2x plus 0 minus 3, which of course is just 2x minus 3. Great. So that's what f prime of x equals. That's what the derivative looks like. So now we can plug any point we want into here, and it'll tell us what the slope of the tangent line is at that point. What we're interested in is what f prime of 3 is. So it's a very simple process now. F prime of 3 is, just plug 3 in. 2 times 3 minus 3, that's 6 minus 3. The answer is 3. So this was a very useful answer here because we can now plug any x value in to get the slope of the tangent at that point, and this is the answer we were actually looking for. Now remember, we could have also answered this by using the highlighted equation right here, because we actually knew what a was in this case, right? If all we wanted to know was what the slope of the tangent was when the a value was 3, we could have gone with this equation or this formula right here, right from the start. But if then there was a second question that said, what's the value when you have f prime of 7, you'd have to do the whole thing over again. Whereas if in this question, if we done it this way and I wanted to know what f prime of 7 is, easy, I just plug 7 in here. 2 times 7 is 14, minus 3 is 11. I'm done. Instead of doing this multiple times, right? Here I did it for f prime of 3. I did it the old way like we did last chapter, and it still works. I still get the answer 3. Check it all out. Check my work. Yay, I got it right. So this answer is the same as this answer, but the power of this is I could very easily find the derivative of other x values, whether it's 3 or 4 or 5 or 6 or negative 8 or 12.2 or pi or whatever. I don't want to have to do this every single time I pick a new value. That's painful. All right, last thing, differentiable functions. A function f is differentiable at a if f prime of a exists, if the derivative exists. That makes sense. And it's differentiable on an interval if it's differentiable at every number in the interval. So it's very easy to tell from a graph where a function is not differentiable. There are 4 things to look for. Number 1, if it has a distinct corner, it's not going to be differentiable. So for example, if it looked like this, what does that suggest is not differentiable? What's this look like? Absolute value. So this right here, this distinct corner right there, that means it's not going to be differentiable if that shows up in your graph. At that point, it's not going to be differentiable. Differentiable all here, 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 not differentiable there. Okay, number 2 is a cusp. So a little sketch of that. A cusp would be something like this. It's not differentiable there as well in this area here. Number 3 is when you have a jump discontinuity. Remember the jump discontinuity? Let's sketch one of those for you. So if we have some kind of function and it's going along here, very good, it's all differentiable, good. Whoop, we jump up here to complete the function, right? There's this jump here, and so in this region here, it's not differentiable. And the fourth thing to look for to see if it's differentiable or not, it's a vertical tangent. So if there's a vertical tangent, it's not going to be differentiable. What would that look like? Let's see, how about something like this? You can imagine if you were drawing tangent lines somewhere around here, there'd be a perfectly vertical tangent line, and so at that point it's not going to be differentiable. So those are 4 things to look for if you have a graph about how to know whether something's differentiable or not. Tell the truth, it's not the most important thing to worry about. What is vitally important is what we're going to be doing for the next bunch of days. So enjoy this video, learn it well, and get ready for the most important part of calculus yet.
Oh my God, I could have died